everybody, and welcome to the second statistics session of the electrophysiology workshop. Today we are gonna talk a little about, as I already said, statistics and so, no, that's the wrong one. This one. That is. Yeah. As I already said, we're going to talk today a little about statistics, more precisely different statistical factor types, like what's a categorical factor, what's a continuous factor, what's the difference between fixed and random effects, and then a number of different modeling techniques like t-tests, correlations, mixed models, and generalized linear mixed models. And then I have a couple of demo cases where we can apply that concepts, and in the end we have a continuation for multiple comparisons when they kind of little brushed last week. And next week is going to be Machine Learning 1, where we're going to talk about the idea of machine learning, what it's supposed to do, what it can do, what you can interpret from the results, how you can train your machine learning algorithms, and what to look out for. So let's jump right into it and start with the categorical and continuous factors. Whenever you build some kind of statistical model, you got to decide whether each individual factor you're observing, the independent ones, whether they are categorical or continuous. Usually, let's say you look at a factor, and the factor has like 2 levels, and may have 4 levels, or may have 8 levels, or may have like a really high number of individual levels. And then you got to decide for yourself in the end whether you want to treat that as categorical or whether you want to treat that as continuous. And you can. Well, first you basically have to look out whether your factor that you want to include in your statistical model is sortable or non-sortable. Because if it's sortable, there's a fixed dynamic behind that factor. Like if you had temperature is sortable, so there's a static frame around the concept. Whereas if you had patients' IDs, you can sort them, but there would not be too much use in sorting them most times. So that's like a more free dynamic. But irregardless, that's always going to affect your dependent variable. And when you do your statistical modeling and decide whether that factor is categorical or continuous, if you got sortable, no, if you got you got to decide what you want to know with your model. For example, if you have your patient IDs and you want to sort them because it's a specific order in which patients were treated. If you sort them, you basically tell the model that the order of the patient, if you sort them as in making that in a continuous factor, you basically tell the model that it's the order of those patients is important. Whereas if you treated them as categorical factors, you would still have your patient IDs, but the order of these patient IDs wouldn't be important anymore. Your model would much rather treat each individual patient as a representation of a specific state instead of increasing or decreasing scale. And the other concept we are having with our factors is whether they are either fixed or random effects. And if you have fixed effects, well, let's start with a fixed effect where we, let's say, have a certain number of levels that this effect can have, and on the right side here we see a distribution of samples we got from this factor. And if we take a closer look at that, we could also decide that instead of representing this distribution with those individual levels, we could look whether we want to represent that with Gaussian, basically assuming that our random effect is normally distributed. And that comes in handy when we take again a look at those patient IDs, for example. Because if you do your statistical model, you want to limit the number of factors you have in your model. Otherwise, you're gonna run into the issue that we had last week with multiple comparisons, that you're gonna have a super large amount of factors, hence you're gonna need this really conservative multiple comparison correction, and that kind of trashes your statistical power. And random effects kind of provide you with an alternative for that. So you could theoretically say your patient IDs were continuous, then it would be one factor, but the order of them would have to matter, which mostly does not. So that would be a bad approach in doing that. On the other hand, if you model them as a categorical factor, but as a fixed factor, each patient, as I already said, would become its own individual state. So let's say you would have like 20 patients in your study, you're gonna have 20 factors that you're looking at. So you just exploded the number of hypotheses you're gonna investigate. And the third option there is to model those patients as categorical, but as random effects. Basically saying that whatever is different between those patients is going to be more or less randomly distributed, and hence it's going to be modeled as one concept much rather than individual concepts for those individual patients, and that's going to sharply decrease your hypothesis count in the end, which will in turn increase your statistical power and making it easier to draw conclusions from smaller sample sizes. Yeah. So to sum that up a little, if you have your independent variable and the variable is non-sortable, hence has some kind of rather free dynamic, you can mostly decide whether you want to model that as a fixed effect or a random effect, and you want to make that a fixed effect if you're interested in the difference between those individual states. If you're not interested in that, it's usually advisable to model that as a random effect, because that, as I already said, decrease the number of factors you're going to have in your model, hence increase the statistical power of your model. Yeah. And then I have a couple of illustrations on how that concepts play out when applied in your actual models. Let's say you did some study, you collected a number of beautiful gray data points, and now we know that which data points are coupled, because let's say the red data points are from the same patient, the blue ones are from the same patient, and so on. Like each color represents a separate patient. And when we want to build a statistical model on that, we can leverage that knowledge. Because if we make that connection, we can basically say that our patients are going to have a certain effect on our model. And if we are just interested in the difference between the left side and the right side here, we can investigate what's the average difference between patients, and by doing that we basically cramp them closer together on the left side, on the right side. So instead of computing the difference between this left side here and that right side here, we would only compute the difference between this side here and that side here. And to achieve that, you would have to model your patients as you would have to include the patient as a factor in your model, either as a categorical factor or as a random effect. And by doing that, as I already said, you're kind of normalizing for the difference in between patients, but it's only normalizing for the difference in offset. So let's say you did an EEG study or something similar, and of course you're gonna have like different impedance on average across patients, and you usually want to get rid of that, and that's where you would apply something like that, because instead of having your impedances like all over the place, you could cluster them together and actually focus on the effect you're interested in this case, left side versus right side. The other thing we could look into when we model our patients in here, again leveraging the same knowledge, is instead of going from the shifting them closer together, we can normalize the slope here across patients. We can basically assume that each patient contributes a different slope. Like you provided the patients with some medication, and some of them is going to work better, and some of them is going to work both, but more or less, let's say all of them have the same trend. So you can basically get, if you again include your patients into your model, you can get rid of that difference in slope here, and can harmonize that, therefore making the effect more uniform, which will in turn then net you a stronger statistical power when you do your evaluation in the end. And then there's of course the concept of combining both of those, and then you would end up with something like that. And I plotted them here a little on top of each other, but effectively they would sit right on the same spot, like all where the green one is. And if you did now a t-test between the pre and the post, you would basically compare this height here of the green one here versus this height here of the green one here, but with the power of the whole group. And if you did not include the patient to normalize for these factors into your model, you would basically, let's say, do your pre versus post comparison on this data here, where you have so much variability on the left side and so much variability on the right side, and also difference in scale in regarding to the fact that you have to have a way higher patient count to compensate for that in the end again. So by normalizing for that, you're reducing amount of data you need to actually see your effects. And then another option that you should look into is, again, if you collected some data points and we know who belongs to who, and what you should also look into is whether there's difference between confounding factors. Like, let's say you did some pharmaceutical study, you provided them with a drug, and some of those patients are, let's say, female, the other are male, and there may be a difference in effect. And if you include gender in your statistical model, and your statistical model compensates for that factor, you would, which in this case here would be, let's say, the red dots versus the blue dots, you could get rid of the difference between those groups, because you're not really interested in the difference between male and female here. You're interested in whether the drug does something or not, and you could get those closer together instead of them being more apart. Then another example was that again, you have a couple of data points and you're looking into again the difference between pre and post, and this time you what was it? This time you you're including more factors to compensate for confounding you're compensating for the confounding factors, like 2 of them going down, a couple of them going up, and you're also compensating for a difference across patients, which then again would yield you statistical model which is again more adapted to your data, which in turn lets you closer investigate the statistical power of the effect you're actually interested in. And yeah, if you put all of them together, you can basically get something like really powerful. Also, we start with this very washed out concept here, and we basically came from here to here by including patients as individual factors, harmonizing across patients. Then we included a confounding factor, which might theoretically be gender or whatever. It depends on what you're looking into. And another thing which should be mentioned at this point is if you want to investigate the difference between pre and post, as you can see here, the gradient points in different directions, whereas for the blue group it goes up, for the red group it goes down. And if you want to investigate whether there's a difference between the red and the blue in relation to pre and post, you would have to look into the interaction between two effects. Meaning, yeah, as kind of a little as the name already says, if I'm with a drug example, if I'm male, does the drug another thing than as if I was female, or the other way around? And that's what you would look into when including interaction effects into your statistical modeling. So the take-home message here kind of is that the closer you adapt your statistical model to the data you're looking at, the more power, the more information you can draw out from the data you have. But on the other hand, you have to be careful that each factor you're gonna include is also gonna increase the number of hypotheses which has to be considered when doing your multiple comparison correction later on. So you've got to be wary on the one hand that you're not including too many factors, basically trying to pull too much information out of your data, but on the other hand include those factors that you think will make a difference, so you can basically have the most accurate representation of the effect you actually wanted to look into. Yeah, and the next thing I wanted to go through is a couple of hypothesis tests, and I wanted to start with the Wilcoxon test. The Wilcoxon test is a test that you could apply if your data is, as the slide already says, not normally distributed, which is kind of often the case if you have, for example, if you had a questionnaire and I would have to choose between a score from 0 to 10, for example, then you could theoretically argue that since my score is limited to from 0 to 10, it can't be negative and stuff like that, my data cannot be normally distributed, although that wouldn't be the strongest example. It could also be that you have multiple peaks in your data, making your data not normally distributed or whatever. And in those cases, you can use that Wilcoxon test. And the question the Wilcoxon test answers is whether the medians of two samples are equal or not. And when doing those hypothesis tests, you always have to keep in mind what the specific hypothesis is you're trying to basically invalidate. So let's say you collected a couple of data points, we sort them, and then for the Wilcoxon test we rank them from, in this case, for data points from 1 to 4, and then we score them. The red data points having a going down, therefore having a negative sign, get a score of 1. The blue ones, always all of them going up, have a positive sign, therefore would get a score of 9. And then dependent on this concept, you would investigate whether the median value between the red ones and the blue ones is different or not. Draw a conclusion from that. Yeah. Then what most of you probably have been using so far is a t-test, which assumes that the data is normally distributed. Yeah, then you can go for the t-test, and the t-test leverages way more information because of the assumption that data is normally distributed. Knowing that the data is normally distributed, we can basically conclude that taking the mean of our sample has actually a meaning. Whereas if the data was not normally distributed, the mean would not necessarily have a meaning. And the same applies to the variance. If the data is normally distributed, the variance of the data has a meaning. This would not necessarily apply for any kind of other distribution across the field. So let's go back to our t-test here, and we have the blue group, we have the red group, and we are interested in whether the difference between those two median values is basically sufficiently larger than the spread of the blue group and the spread of the red group. And if you recall the example from the beginning where we normalized for patients, where we had such a large spread in between patients, we would have now a super large spread for the red group and the blue group. And as you saw, the gradient wasn't super strong, so you would have a small difference between the means. So if you would just have done a t-test on that data, you probably wouldn't have gotten a statistically significant result. And that most likely would have to be attributed to the fact that your data was the model wasn't really adapted to the data at hand. And another concept you're probably familiar with is doing correlations, which is basically taking a bunch of points and then drawing this nice straight line here, and that if you go for Pearson's correlation coefficient, usually assumes a linear relationship, which means increase on one axis scales linear with increase on the other axis. If the relationship you're investigating between your two dimensions was not linear, you could also go for either a Spearman correlation coefficient, which wouldn't look at the actual values anymore, but would much rather look at the height of those values and then rank them, and then basically say whether the lowest ranked value on the x-axis corresponds with the lowest ranked value on the y-axis, and so on. And by via that approach, you basically get rid of the requirement of having a linear relationship between your data. But if you know if you plot your data, for example, and you can see what kind of shape that relationship is, you can also try to model that through a function and then try to linearize your data via that function. And afterwards do the correlation to investigate whether there's significant correlation between those warped data sets or not. And the last approach I wanted to present here is using generalized linear mixed models. And those usually are the most complex one in terms, well, they're way more complex than all the other approaches I've discussed so far, but they are also the most adaptable ones. And there's a number of factors in there that underline that flexibility. For example, if you did your t-test or your Wilcoxon test, you are usually limited to basically observing. You have to have independent observations, and they have to describe a common dependent variable. So if you had like 10 patients, you can take one data point from each patient. You cannot take more with your t-test, otherwise you would repeatedly measure within the same patient and hence invalidate your t-test. So you are limited to a single sample because, let's say for random reasons, we consider patients to be independent. And so you are limited in the amount of data you can actually include into your model. Whereas if you did, I have to say the same applies to the Wilcoxon test or correlation. But if you did the linear mixed model or generalized generalized linear mixed model, or for example an ANOVA, which is quite similar to a linear mixed model, you can include those repeated measurements factors into your data. You can say that I measured repeatedly across each patient because, let's say you did some EEG measurement, those have a tendency to be unreliable, so you got a large number of individual data points from each patient. And you don't want to average across those data points because that means throwing away a lot of data. You want to include all of them. And if you want to do that, you have to go for a linear mixed model or a repeated measurements ANOVA. And the repeated measurements ANOVA or any type of other ANOVA is already a kind of more flexible version of the t-test basically. And those would already allow you to include more factors into your model. And if you want to have like basically the full range flexibility at your disposal, you're gonna have to go for linear mixed models, and with them you can basically more or less freely decide on you can arbitrarily decide on how many factors you're going to have in your model, how those factors are going to interact with another, whether they depend on one another, whether there's an interaction between those effects, and yeah. But the kind of drawback from that is, of course, that applying generalized linear mixed models or linear mixed models is a little bit more complicated. But the next slides are going to contain a couple of demos for those. Anyway, the last thought in the linear mixed models is that usually they require the dependent variable to be normally distributed, which of course is not always the case. And if that's not the case, you can basically apply the generalized linear mixed model, which then would say that your data might be Poisson distributed or binomially distributed if you are looking into something that's usually has a binary outcome. Yeah. So I prepared a couple of examples and I'm just gonna read them out, and then I'm gonna give you some time to think about what factors are in there, and then we are gonna model together how to ideally describe the questions we're interested in. In the first demo, there was some data acquired for a study. We measured a couple of patients prior and after an intervention. We know nothing else, which is kind of convenient, which means there's not really much we have to include in our model. And we are interested in whether the intervention had an effect on the patients or not. And as I said, I'm just going to wait for like 15, 20 seconds, and then I'm going to reveal the factors in there. So in this example, we of course have patients because we measure repeatedly across patients. We have an intervention, which is the very variable we are most interested in, and now we got to build a model with those factors. And the question is basically, how does the outcome relate to the patients and the intervention? In this example, outcome can be described as the effect of intervention and patients, for example. And if you would apply this model, you would basically look what's the effect of the intervention on my patients and what's the difference between patients. But as I basically kind of indicated a little earlier, this one is gonna run into issues because you have to estimate a different effect for each patient. So if each patient was measured twice, it's hard for the model to accurately predict then in the end what's the difference between patient 1 and 2, 1 and 5, 1 and 7, because there's a lot of variability and very few data points to compensate for that. So what might be a little better is if you looked into the effect of the intervention, and then you could model patients as a random effect. And that would basically net you a stronger statistical model, because you're not looking into the difference of each individual patient anymore, therefore not treating each individual patient as a separate state, but rather, as I explained, put them together into a Gaussian distribution of patients, treating them rather as a cloud than individual points. And then you would still get, with this example, you would get rid of the offset in between patients. And would be able to look at the intervention. With this example here, you could look whether, again, what's the effect of the intervention, and we have allow those patients to have an individual offset. And if we put the intervention here, we would even allow each patient to have a different slope again. Like in some patients, the intervention has a stronger effect, and some of them it has a weaker effect. For all of them, it would have to point in the same direction, of course. Otherwise, you would not get a significant result. But the strength of that gradient wouldn't have to be necessarily the same in all of them. It would suffice if it's somewhat similar. And with that model, you're gonna have a similar issue that with this data acquisition protocol here, you're likely not gonna have enough data for this model, because there's too many factors in there. So what you want to do with this one, ideally you want to go with the second model here. Although you could also go with the first model if you're lucky that the difference between your patients is not too large for and the model's not stretched too far with that. And that's kind of the interesting fact with those rather advanced methods in statistics. If you don't do something rather simple like a t-test, you're always going to have to ask yourself, what kind of model do I apply and how do I want to combine those factors? And usually there's no right or wrong approach. All three models are totally valid models, and none of them is inherently flawed or wrong. They have different necessities, like they need more data, they need less data, they're gonna come with a higher hypothesis count, they're gonna have a smaller hypothesis count. So when investigating those, whatever the facts that you are interested in, you always got to make sure that you know what you're looking for. You know how you would expect those factors to have some effect on one another, and if you apply a certain model, you should be aware of what you can conclude from the model. For example, if we applied that second model here, which is totally valid, we would not be able to tell whether there's a lot of whether there's a significant difference between patient 1 and patient 5, because we're not investigating that in the first place. But we get stronger statistical, in turn we get a stronger statistical power on the effect of the intervention, likely. So there's always these advantages and disadvantages when selecting those individual models. And then I have another demo here in which more data was acquired for a study. Patients were evaluated at several points this time throughout the study. There were several interventions which may have had an accumulative effect, and we are interested in again what if was the effect of the intervention of the patients. So what are the, just gonna wait a little, what are the factors you would model here? this time we'd have the patients, we had the intervention, and we have the additional factor time, because we are measuring those patients repeatedly at several points throughout our study. So we're not only having pre and post, did that a couple of times. And then, of course, we gotta conceptualize how those three independent factors then again affect our dependent factor. And again, as with the other one, there are a couple of options. We can either treat them all as normal fixed factors. Then in this case, we would have to ask ourselves, do we want to make the intervention an categorical factor, or do we want to make it a continuous factor? Because from the description we know that we expect the interventions to have an accumulative effect. Hence, sorting them into intervention 1, intervention 2, intervention 3 would make sense if that's actually the case. So we could basically think about making the intervention a continuous factor in this case if we wanted to. Then again, we have the patients, because there's difference in between the individual patients we are looking into. And this time we also have time, because we're measuring repeatedly across our patients. And then we basically have a number of different models we can apply. We can say that time plays a role in here. And if we say that time plays a role, the question is, do we want to investigate the effects in between different time points? Is that actually something we're interested in? Or are we just going to say we measured repeatedly across time, and there's going to be some effect of that, but we're not really interested in that, which would be that random effect here. Random slope in this case. Random offset. And then the same applies to the patients. Are we interested in the difference between patient 1 and patient 5, or can we simply say our patients, let's say, have a different offset? And then we, of course, can do the same thing for both factors. We can say there's some difference in between patients, there's some difference across time. I'm not really interested in either. I'm just going to be interested in whether my intervention does a thing or not. And then, of course, we can again think about whether the effect of the intervention does have the same slope across patients, whether there's a different slope across patients, and how that might play a role. And again, none of these models would be inherently flawed at this point. It's about the conclusions you can derive from these models. For example, if you applied, let's say, the second model, and then you would say at time point 2 we have a different effect than at time point 5. That's not something you could deduce from this model here anymore. Therefore, you would have to run the first model or the third model. So, again, choosing which model you want to apply is more or less a question of how much data is available, and what kind of information do I want to extract with that data, at which cost. Again, more factors need more data, gonna net you a lower statistical power, but on the other hand, the better you adapted your model is to the data at hand, there's also the chance that your model might yield to a higher statistical power, because you're compensating for the right factors driving variability in your data. And then I have a third example here. Let's say we do a candy study. We give some patients a red candy, some patients get blue candy, and we are interested in what the candy does to the patients. And then again, the question would be, what kind of factors would you identify when having this set up? And with this setup, of course, we have our intervention, giving the patient candy. We have the individual patients, and we have the candy type, being red candy or blue candy. And then, as with the other two examples, the question is, how do those factors relate to the dependent factor, the effect of the candy? So in this case, we could, for example, look into what's the effect of the intervention, giving the patients candy. And again, in this example, we wouldn't be interested in what's the effect across different patients. We just want to let the model know that we repeatedly measured across patients, hence compensate for that. Then theoretically, we could be interested in whether there's a difference across patients, but data for that is a little scarce here. And then, of course, we can look what's the effect of the candy type. Like, is there a difference between giving them red candy and giving them between the red candy and the blue candy in general? And then we could include the interaction, which would be the combination of, was there a difference between those patients that was given that they're given red candy and those patients that they're given blue candy? Like in terms of a clinical study, that would be if you provided your patients again with a drug, was there a difference between those patients that are that got the drug and are female and those that are male, or whatever confounding factor you may expect? And then again, as with the other stuff, all of those models are valid from the start. There's no inherently invalid model. It again depends on what you want to look for in those models and what kind of information you want to derive from those. And the last topic for today's session is going to be the completion of multiple comparison correction. Last week we already established that not going for multiple comparison corrections, if you go for alpha value of 0.05 and do like 50 hypotheses, nets you an almost, I think it was like 90% chance on having at least one of those false positive. And that really comes into play when you do those clinical questionnaires that have like 20 or 30 subcategories. You have 20 patients. You statistically evaluate each subcategory and you're gonna find something. So you're gonna have to correct for that multiple comparisons. And one method of doing that is the Bonferroni method. And the Bonferroni method looks how many hypotheses you have in your scope. It takes the alpha level and then it divides the alpha level by the number of hypotheses. So let's say you published a paper and the sole content of the paper was that single questionnaire with 20 questions, 50 questions in this example. And you want to go for a p-value of 0.05. You got to divide that 0.05 by 50. And if you applied this value of 0.001, that would effectively mean you applied a value of 5% for the overall paper. And with that multiple comparisons, you basically have two issues coming in. If you have a really large hypothesis count, it's going to be really hard to still have significant results. And on the other hand, the second issue is what do you define as a scope? Because usually with those 50 tests, you could say all of them are independent, and then the number of tests you would have to correct for is 50. But if those tests they are dependent, or there was some common factor among them, 50 wouldn't be necessarily the right number to correct for. It would be lower, because that is 50 assumes that all of these effects are independent. So you gotta keep that in mind, but usually I think it's advisable to just go with a conservative approach in that case, and if you want to go for the Bonferroni method, just say it's gonna be 50 and assume them to be independent. It's more conservative than assuming some false dependency. Then another option would be the Bonferroni-Holm method, which is slightly similar, corrects for the same concept, and but it's going to yield you a little more statistical power in the end. But again, it controls for the family-wise error rate, which means throughout the scope that you defined, like your overall paper, the likelihood of having at least one false positive is then, let's say, 5% or whatever alpha value you selected. And then the other method of controlling for multiple comparisons would be doing a false discovery rate correction. And this time, instead of reducing the likelihood of that error rate to 5% across the whole scope, you go basically, you approach the issue a little differently. You say, I'm going to accept that 5% of my positive findings are going to be false. So you're going to accept a certain number of false positives with those false discovery rate correction methods. But since they are not as strict, they're going to yield you a higher significant power, which means not power. They're going to need you more little more insight, because if you apply the pure Bonferroni method, which is really conservative, you would basically flag a high number of true positives erroneously as false positives, and with a false discovery rate correction, that's less likely to happen. But the drawback, of course, is that there may be one or two false positives in your data in the end. So you gotta decide for yourself what's more or less acceptable for you. Yeah, that's it for this week's session, and next week's session will be Machine Learning 1, where we're gonna look into, as I already said, different machine learning approaches, how to train those, how to validate whether those present good results or not. Yeah, and I look forward to seeing all of you again.